All right, let's come to the second part of my lecture about quantum enhanced clocks. And I need to press here. Yes. Why do we want quantum enhanced clocks? I will give you a brief motivation and then show you the aluminum quantum logic clock, and then two techniques that use quantum stuff, yeah, to make clocks better in the end. One motivation has to do with the type of atomic clock species that we would like to have, because as you know, the periodic table is very large. Yeah, so in principle, there's a very large number of clock species that we could choose from, and the question is, yeah, what's a good clock atom actually? And what would your wish list be for an ideal clock atom? We learned about stability, so it's optical transition. We learned that narrow line width, long excited state lifetime. We learned that's for statistical uncertainty to make that better. But how about systematic uncertainties? Yeah, these possible shifts of the electronic energy levels. What are the advantageous properties that you would like your clock atom to have?
Non-radioactive.
Oh yeah, there's compromises you have to do.
Cheap and abundant. Cheap.
I'm not sure. You don't need a lot of material, actually. Yeah, I'm not sure that's really a mandatory requirement that it's cheap. Actually, fun story I can tell you. Yeah, so we are also doing clocks with highly charged ions. And theorists really do like californium 15 plus because it has a huge sensitivity to a change in the fine structure constant. And then my team started researching where to get californium. And at the time, it turned out it was the most expensive material on Earth. Yeah, you could buy for money. Yeah. In the meantime, unfortunately, it has been superseded by antimatter. That's even more expensive, apparently. Or californium became cheaper because it's more abundant. I don't know. Yeah. Anyway, that's about the cost. Yeah, it's not really relevant, I don't think. Yeah.
So maybe you would like to have less thermal fluctuation.
Thermal fluctuations. So we do laser cooling typically, yeah, to get rid of the thermal fluctuations. But that's a good point. You want it to be laser coolable typically, yeah, to get rid of these thermal fluctuations. That's one thing.
Heavy.
So heavy helps, yeah, to get rid of any Doppler shifts. That's a good argument. And then maybe the most important point, so this is high stability that we already discussed. Then now we're aiming towards high accuracy. So low sensitivity to resonance shifts. One of them is heavy, laser coolable. Then we do not want to have collisions. There's a collisional shift that you can have and they interact with each other. This is a problem in neutral atom clocks. Doppler shifts, so you want to cool them and have them heavy. And of course, you want a low sensitivity against shifts from external electric and magnetic fields, because these are fields very difficult to control typically, and therefore are a limitation. Yes?
What about ion trapping?
Come to that. Yeah.
Oh, okay.
A little bit. Yeah. Okay, so this is our wish list, and then there's very many species to choose from. There's a number of species that have been investigated already. Currently, I would say that in the neutral atom community, strontium and ytterbium are the most commonly investigated species. And in terms of ions, probably all of these, yeah. Lutetium plus is missing here on this slide. So lutetium has been added to the list. And of course, there's many more species to choose from. And maybe there are species that do not obey all of these criteria, but you still want to investigate. And there's not only the front row of the species, which is a neutral atoms, and then one row behind them is the singly charged ions, but there's more. There's highly charged ions. Yeah, this is all the rest. Yeah, and that animation goes for a while. There's so many of them, and there's predictions that there's very good clock candidates with very interesting properties hidden in that large amount of atoms that one could possibly investigate as clock atoms. And there's, of course, molecules. Yeah, why stop with atoms? There's also molecules you could investigate, making this even a larger selection. There's typical systematic effects that we should consider. There's electric and magnetic field effects that can be down divided into more effects, for example, black body radiation shift. Who knows what the black body radiation shift is? Who has an idea what that could be? Black body radiation, I'm sure you've heard, yeah? Every body at 300 at any temperature, yeah, emits thermal radiation, which means that since we're surrounded by walls that have roughly 300 Kelvin, this room is filled with black body radiation. And that is not small. It's 830 volts per meter. That's a huge field, actually, and leads to what we call AC Stark shifts. So the square of that field is an intensity, and that intensity interacts with your favorite level structure, with your atom. And through the polarizability of the atom, typically of the ground and the excited clock state, and that can shift the black body radiation, then shifts these levels. And that's a serious limitation in most optical clocks, actually. Yeah, that you need to control. For example, just an example, in the strontium lattice clock, they need to control the thermal environment down to 10 millikelvin. That's incredibly hard to do or even to measure. They need to calibrate the temperature measures and they measure temperature sensors, and they need to make sure it's homogeneous to that level, and that there's no other hot or colder surface that the atoms actually see. So that's really difficult. And it's an AC Stark shift. Yeah? There's also other AC Stark shifts from the clock laser, for example, or cooling lasers if they're on. In trapped ions, there's also the electric quadrupole shift that I'm going to tell you a little bit more in one of the following slides. Then there's magnetic field shifts, there's Zeeman shifts, there's a linear Zeeman effect, then there's a quadratic and higher order Zeeman effects. So you need to know the atomic response to these fields typically very accurately, the atomic coefficients, and you need to know the field very accurately. There's also relativistic effects. There's time dilation. Time dilation is a second order Doppler shift, as we call it. It's essentially the twins paradox. A moving observer, time passes slower than one who's standing still. And so if you have a twin sister, you send her off on a spaceship with near the speed of light and she comes back, you'll be dead, yeah? Because for her, the time passes much slower. And so it's for atoms. If they're in thermal motion or in a driven motion, then time passes slower for the atoms, shifting its unperturbed resonance frequency, and you need to correct for that. Then there's the gravitational redshift that we've already discussed. You need to know the height of your clock down to the centimeter level from an abstract geopotential equipotential surface. It's called the geoid. That's the equipotential surface of the Earth that is determined by the geodesy people from these potato-shaped Earth, the satellite missions that I've been talking about in the first part of the lecture. And since their evaluations tend to change the value of this reference equipotential, the metrology people have said, okay, stop that, yeah. We don't want this to change. We just fix it by a number. And we just say, okay, this is the number, and everybody references their system to exactly this equipotential reference surface. And this is how it's done. Yeah. So if you do clock comparisons, no matter how far apart they are, you need to account for the height of your atoms above this equipotential surface. And this is determined by the geodesy people in the end.
Regarding the time dilation, that's also true for trapped particles, right?
Yes,
So
they're still
moving, right? And then it's about the width of the wave function in the
trap. There's interesting things to consider. This is now going into an almost philosophical discussion, but yeah, let's do that. Yeah, why not? Since you mentioned it, yeah. So the time dilation shift comes from the kinetic energy of the system. If you have a trapped particle typically the easiest way to trap is in a harmonic oscillator. Harmonic potential, it's described as a harmonic oscillator. So you have a single particle that moves about in the potential of your harmonic trap. You cool it down using laser cooling in the absolute ground state. Is there still kinetic energy in the system? Is there?
Some people said yes.
Yes, there is kinetic energy. It's called the 0-point energy in the system. That's still half potential and half kinetic energy, like in the rest of the harmonic oscillator. And now the question is, does that kinetic energy actually contribute to time dilation? I mean, we cannot cool it away. Yeah, it's always there. Does it contribute? Because actually, if you look at the wave function in the ground state, there's no motion really. Yeah, I mean, it's a Fock state, and it's the ground state of the oscillator. Does it still contribute?
Show of hands, who thinks it contributes?
That's a good point. Yeah, who thinks it's contributing? Yeah. This was induced spontaneous hand raising, yeah, because they saw the PIs raise their hands. Indeed, it does, yeah. And of course, that contribution changes. Well, first of all, if it's warmer, yeah, if you populate more than the ground state, more excited state, yeah, then you get more kinetic energy. But it also changes with your trapping confinement. So the stronger the trapping confinement is, then the more kinetic energy is in that one half h bar omega of the ground state potential. And so the tighter the trap, the stronger the time dilation becomes. And then you can think, okay, and then there's another effect. There's a width to the wave packet in the harmonic oscillator potential. It has a certain width in the harmonic oscillator potential. And then you can think, okay, there's a gravity gradient across this width, yeah? Because you have to hold it against gravity, and then there's a gradient across that thing. And that when eventually the gradient becomes so strong that across the wave packet size, yeah, it becomes comparable to the second order Doppler shift. And then people have drawn up a trade-off, yeah, where both are equal in size and of the same order of magnitude. And it turns out that it's a trapping frequency of a few kilohertz, I believe, yeah, if I remember correctly. Then the uncertainty due to the position spread in the gravity potential and the uncertainty from time dilation is the same. So these are unrealistically small trapping potentials, and that's not the point, yeah? Because we can measure trap frequencies and the associated kinetic energy to sufficient digits that this is not an issue. Yeah, it's like any other systematic effect. We calculate its magnitude and then we subtract it. Yeah, so the time dilation shift from 0-point energy has to be taken into account. It's never a limitation, at least up to now. Yeah, an interesting question, although still remains: what happens with gravity, if gravity stretches across the atom? So if there's the atom has a size like a Bohr radius, for example, yeah, And then if there's a gravity gradient across the electron orbital, what happens there? How do you calculate this? Yeah, I don't know. Yeah, that we're a couple of orders of magnitude away from this, but it's an interesting question to ask. That was a detour on gravity-induced effects. Then there's collision shifts that I already mentioned that need to be characterized. Yeah, please.
Could you then model the system like, let's say, there is magnetic field, there are Zeeman sublevels due to magnetic field. Could you then model the system? Let's say there is a magnetic field, there is a gradient of the gravitational potential across an atom. Could you model your system like it is in a magnetic field? You have different sublevels, let's say, on top of your electronic sublevels, or you're trying to measure, let's say, a Zeeman sublevels or stuff like that. Could add more.
I do not think that this will lead to a level dependent shift. Probably not. Yeah. Because the conception I have trouble with, but I think that's just me, yeah, is that time goes slower for the part the electron spends in the lower part of the orbital than the time it spends in the upper part, yeah, and that would lead to an average change in the time evolution, but maybe that's just a constant if you have a symmetric distribution around the nucleus, for example, or the center of mass of your atom. So I do not think that leads necessarily to a level-dependent shift. Yeah, it's, if at all, an overall shift of the time evolution. But I still think it's an interesting question. More questions on this? If not, I've already mentioned that for most of the systematic effects that we have to deal with, and I will give you an example how all these effects look like and what they are limited by for the aluminum clock. But most of them are evaluated in an error budget table typically, and they have typically two contributions. So that's the uncertainty of type B, systematic shifts. And here's the example of the black body radiation shift, again, fractional frequency uncertainty. And then you have the typical error propagation, where you have two contributions. Yeah, the shift itself is the polarizability times the electric field squared. And if you do Gaussian error propagation, then you get the square of the relative contribution from the polarizability, that's the atomic property that you only know up to a certain uncertainty, plus 2 times, because it's squared, the electric field, the relative uncertainty of the electric field. That's essentially the temperature of the environment that the atom sees. And that's also something that you need to measure. This is something you can control, and this is something you can either calculate or also measure independently, the atomic properties. But it's always these two contributions. Okay, now to make really good clocks, we need to apply quantum technology 2.0, as people call it. Yeah, you need to control all relevant degrees of freedom. You need localization, because if they're not localized, yeah, you get, first of all, recoil shifts from absorbing and emitting photons, which you don't want during spectroscopy. And you would get linear Doppler shifts that I mentioned at the beginning of the lecture. Yeah, if the atom would just move away constantly, that would introduce a Doppler shift, a linear Doppler shift that you don't want. You want laser cooling to minimize the second order Doppler shift, and trapping then, of course, your atoms. You need to have exquisite internal state control, which you can achieve through optical, radio frequency, or microwave interaction. And then there's 2 main types of clocks that we have. The first are ion traps. They're kept in spherical or linear Paul traps, where we apply radio frequency fields on these blade electrodes here, and a positive DC field here at the end cap potentials. And all in all, that generates a 3D harmonic confinement for charged particles, namely singly or multiply charged ions in the trap. The advantage of ion clocks is that they have very few and typically very small systematic effects. Whereas when we look into optical lattice clocks, where the atoms are kept in a standing wave light field of an optical lattice, there you can already see from the picture you have hundreds to thousands of atoms at the same time. You get a much better signal-to-noise ratio at the expense of larger systematic frequency shifts and uncertainties, yeah, that you have to deal with. Okay, and so what I mentioned is that we need to fulfill all these requirements here to make good clocks. So first of all, we need to select atoms that have a very small atomic or a very small susceptibility against external fields. Polarizability should be small. The Zeeman shifts should be small. They should be heavy, laser coolable and trappable and so forth. Yeah, so we need to fulfill all these requirements. And now, reminding you of the periodic table that I've shown you, not all of the species in that periodic table can even fulfill these very basic requirements that we can laser cool and detect them very efficiently. And this is where quantum logic comes at the rescue. And I want to show you the aluminum clock as one of the first and prime examples of how we can use quantum techniques developed in the context of quantum information processing with trapped ions to actually enable an optical clock based on aluminum that has very favorable atomic properties. That has been identified actually as a good clock atom by Hans Dehmelt in 1992. Here's Hans Dehmelt with the insert of a penning trap sitting there and the picture of a single ion on top of his head in the background. He identified aluminum as a preferred clock species because it has a very narrow optical transition of 8 millihertz, 20-second excited state lifetime. It has no electric quadrupole shift. That was actually his main motivation because it's a J equals 0 to J equals 0 transition. So these states do not support electric quadrupole moments, and therefore you do not have an electric quadrupole shift in aluminum. As it turned out later, we actually found that out when I was at NIST and we built the first aluminum clock, that the black body radiation shift is, at the time, it was the smallest of all atomic species investigated. Yeah? So it's super small and not a limitation in our typical clock. The problem with aluminum, though, was that the first dipole allowed transition that we would use for laser cooling and doing this detection scheme is actually at 167 nanometer, where we do not have lasers yet, at least not simple lasers. And therefore, it took about from maybe 15 years or so until the first aluminum clock was built using these quantum control techniques. The idea is that has been conceived by Dave Vineland to trap aluminum together with a logic ion species. In our case, we use calcium as a logic ion species. And due to in the same potential of an ion trap and due to the Coulomb repulsion, they interact very strongly with each other, and their motion has to be described in the form of normal modes, like you know from solid state physics. So if I push on the calcium ion, then both ions start moving around, like they're coupled through a very strong spring, which means in turn that if I cool the calcium ion, which I can cool very efficiently, I also cool the aluminum ion, and so that works very well. Going one step, so sympathetic cooling can be provided by the logic ion, and I can use the logic ion to read out the internal state from the aluminum ion after spectroscopy, because I cannot do this electron shelving technique in aluminum directly. So I have to do a coherent mapping of the internal state information through a series of laser pulses onto the calcium logic ion, and there I can do then the detection. And in a very similar fashion, I can use the calcium ion to actually prepare the internal state of the aluminum ion also. So all dissipative parts are moved over to the calcium ion, like cooling and internal state preparation through optical pumping, and I only apply coherent operations on the aluminum ion. And so they form a composite system that combines the excellent controllability of our logic ion with the interesting clock features, the insensitivity to external fields of the aluminum ion. And that was the first, but is in the meantime not the only example of quantum logic spectroscopy. There's also highly charged ions that we work with in our group in a close collaboration with Jose Crespo and his team. And in the meantime, more and more groups are starting experiments in that direction. And then molecular ion state detection, preparation, and spectroscopy. We also did the first non-destructive state detection of a molecular ion. And in the meantime, others have followed suit and pushed it even towards spectroscopy, in particular in this group. Okay. Now, I mentioned that sympathetic cooling is not an issue. Here is not the aluminum clock as an example, but this is a nice movie to show. So what you can see here in the false color image is a live recording of magnesium ions fluorescing under laser cooling in a linear Paul trap. That's why they line up in a string. And here you can see the dark spots moving around. And these are very likely magnesium hydride molecules. Do you know why they jump around here? That's a real life issue, a real time movie actually. Why do they keep moving around? Any ideas what could happen here?
Tunneling, maybe just through the trap, tunneling from one side to the other.
Sorry?
Tunneling from one side of the.
No, tunneling. These are 5 microns apart. So tunneling is prohibited. Yeah, it's very strongly suppressed. I give you a hint. We had a leaky vacuum window. Now, any ideas? Yes. So the correct answer is collisions with the background gas atoms because we had a leak. Yeah. What you don't see is because it happens so fast that upon a collision, the entire crystal melts and is almost instantaneously recooled because Doppler cooling is so efficient that you don't see that. But of course, then the crystal reorients every time you do that. But what you can see here, and that's my main point, there's a very well-defined dark spots here. So the ions are localized, which means that they're also very cold. And that can and has been confirmed in clock operation as well. So that's a mostly solved problem. Now, how can we do the state transfer from after to implement the readout? And that idea dates back to a seminal paper by Peter Soller and Ignacio Cirac at the University of Innsbruck from 1995, where they proposed to do quantum information processing with trapped ions using the normal motional mode, the joint mode of motion, as a quantum degree of freedom to implement gates between the two ions. And in that paper, they proposed the famous Cirac-Soller gate, and that actually kicked off quantum computing with trapped ions that has come a long way, as you can tell. When you watch the media. Now, the main idea here is that there's collective motion of the two ions that we can treat as a quantum mechanical degree of freedom and address individually using laser radiation. And it was Dave Wineland who had the idea to implement that for making spectroscopy better. How does that work? Let me give you a brief theoretical introduction on the system. In the simplest case, we have one motional degree of freedom that could be the center of mass motion of the two ions in the trap or the in-phase motion. And so that's a corresponding harmonic trapping potential with the harmonic oscillator spacing. And then we have our two-level system, which could be a clock transition, for example, where the excited state is metastable. So the line width here of the transition is much narrower than the spacing in the harmonic oscillator. And typically the spacing in ion traps is on the order of a megahertz. So it's very, very stiff traps. So that combined system looks like this. It's a ladder system where you have here the electronic ground state, the electronic excited state, and then there's all the motional states on top, which we can fan out. And then we have a numbering scheme, spin down, and then N denotes the motional quantum number, and we can drive transitions between all of these levels by appropriately detuning our laser beam. So if you look at the zoom in here to the ground state manifold or near the motional ground state, then we can drive what we call carrier transitions. If you're resonant with the electronic transition energy between the two levels, that only changes the electronic degree of freedom, but not addresses the motional degree of freedom. We can then detune, because we're in the resolved sideband regime here. That's this condition here. We can detune the laser to address what we call a blue sideband, where starting from the ground state, we go into the electronically excited state and put in a quantum of motion at the same time. And we can choose that by simply detuning the laser by exactly one trapping frequency, which is on the order of a megahertz. We can do the reverse, which is a red sideband, where we go from the ground to the excited state and remove a quantum of motion by red detuning by exactly one quantum. And now, of course, you can already tell that we can use these red sidebands to cool all the way to the ground state. Because if we then drive red sidebands, and reinitialize to the electronic ground state, and then again drive a red sideband, reinitialize, drive again a red sideband, reinitialize, then from here, that's a dark state. There's no level to couple to, which means that if we apply these pulses, all the population will accumulate here, which is the motional ground state. And that's actually how we do it most of the time. Okay, now you have all the ingredients to understand how this quantum logic readout protocol works. We start by both ions, the calcium and the aluminum, in the electronic ground and electronic motional ground state. We then apply spectroscopy light on the aluminum that in general generates this superposition state that I was talking about earlier. Now, for a regular clock, you would now detect using this third level, which we do not have available in aluminum. What we do instead is we apply this red sideband, which, starting from the motional ground state, only can address the excited state population, transfers it down into the electronic ground state while exciting one quantum of motion. The ground state motion, because the red side, there's no n equals -1 state, has no level to couple to and is therefore untouched. So in essence,
No, just this light is 167 nanometer.
No, that's the clock light at 267 nanometers. That's the clock transition, we never have a laser for 167. That transition is never driven. So this is really 267 nanometer clock transition in the aluminum ion that we use here. And so what we've done through this red sideband pulse, the computer information guys would call it a swap gate between the electronic and the motional degrees of freedom, because we've turned this electronic superposition into a motional superposition of the ion crystal, because it's the shared motion of both ions, it's a normal mode, of being in the motional ground state and the motionally excited state here, the n=1 Fock state. And now, since this is a shared mode between both ions, we have essentially provided the aluminum with a kick, that then turned the ion crystal into motion. We can do the same in reverse on the calcium ion, apply a red sideband, and then turn the motional superposition back into an electronic superposition, but this time in the calcium ion. Please, microphone.
Since you said the computer scientists would say swap gate, so is the aluminum itself already 2 qubits?
Yes. Grounded and excited state, this is a qubit essentially.
Yes, but is it 2 qubits already?
No, it's 1 qubit. Yeah.
Yeah.
So we have a 3 qubit system here. One is the aluminum ground and excited state. These are the qubit states. We have the motional degree of freedom, the ground state and motionally excited state is another qubit. And then the third qubit is the ground and excited electronic state in the logic ion. So it's 3 qubits, and we do pairwise a swap gate. So we implement a swap gate between aluminum and the motion, and then a swap gate between the motion and the calcium logic ion.
Yeah, perfect. Thank you. Yeah.
And in the calcium, we have all techniques available to read out. We can apply this shelving transition and therefore determine the state populations that are a faithful copy of what had been the states in the after the spectroscopy light. And that works extremely well. So we can scan across the aluminum resonance frequency here. This is a detuning in hertz. So we put the 0 at the line center here. You can see here the clock state change probability, or in simplified terms, an excitation probability here as a function of the frequency using exactly, or a scheme very similar to this scheme. It's not exactly the scheme, but very similar to this one. Okay. Now, in reality, again, things are not as simple. Yeah, there's a little bit of overhead here involved. I showed you already this part where we do laser cooling, state preparation, clock probe, and then detection, the detection sequence. And we do that, of course, for the F plus and F minus on each side of the resonance, where I showed you how the clock feedback cycle works. And we do that for different initial states. So this is the expanded level structure. Aluminum 27 has hyperfine structure in ground and excited state. It has an F of 5/2, and so we have here 6 levels in the ground and the excited state that depend on the magnetic field, of course. Yeah, so there's a nuclear Zeeman effect here that we need to take care of, and for this reason we do probes on this stretched state, the minus 5/2 states, and on the plus 5/2 states. And if we do the average of both, then we get rid of the linear Zeeman effect. The average is then free of the linear Zeeman effect. And if we take the difference, we get actually in the magnetic field, which we need to know to determine the second order magnetic field corrections, second order Zeeman shifts. And so we do not actually lose signal to noise ratio here because every single measurement contributes to averaging down in the end. Okay, yeah. Then what I did not mention is that there's also interleaved measurements. We do not only run the clock cycle as shown here, but we do some monitoring experiments. For example, we check whether the temperature is still close to the ground state as it should be, or whether the laser cooling parameters have gone off and we don't cool efficiently any longer. We need to make sure that this does not happen. And so we need to do service measurements to ensure that. We also need to compensate for stray electric fields that might build up over time and make sure that the ion is always in the trapping center. And we can probe that using these service measurements to always bring it back to the center of the trap where these excess shifts are significantly reduced. And that's 60% duty cycle means that 60% of the time we run this, or we actually 60% of the time we probe the clock transition, so we're sensitive to frequency shifts, and 40% of the time we do all the rest, including interleaved measurements. So running the clock is, I mean, it's also not simple, yeah, but you can achieve that very quickly, yeah. Then the more elaborate part is compiling an uncertainty budget table, such as this one here, where you investigate all possible frequency shifting effects on your F0. That's the gap between the unperturbed transition frequency and the frequency that your apparatus actually gives out. So here's the shift effect. The shift that we have measured or calculated and applied to correct the frequency to the unperturbed transition frequency. And then this is the uncertainty with which we can apply this correction, yeah, this correction here. And as you can see, the correction is fairly large. It's dominated by the quadratic Zeeman effect in the excited state, because there's more hyperfine states that our clock manifold couples to, and that distorts the levels when you have a non-zero magnetic field. And this is the largest correction that we have to apply for. And then the second largest is, again, a quadratic Zeeman effect, but an AC from the trap drive field. So we drive the trap with an RF field, and that leads, of course, to charging and discharging currents that produce a magnetic field that also has to be taken into account here. Yeah. So these are the shifts here and the corresponding uncertainty in decreasing order of uncertainty here, as you can see. And we're now at roughly 1.4 times 10 to the minus 18 systematic uncertainty by summing up the squares or the mean square sum of all of these shifts. Now, let me go through some of the shifts. We do apply a cooling laser during interrogation. I think that's, yeah. No, I'll show that later maybe. So what the specialty in our system is that we apply a cooling laser on the calcium during clock probing, which we can do because we have divided the task of being a good clock ion and controlling motional shifts onto two ions. So we have the clock that is then can be sympathetically cooled by the calcium while it's being probed. Please.
Regarding this, the entire approach of using two different atoms essentially as a system for cooling. So so when we are trying to cool calcium, let's say it is in a like a bonded state with atom we are trying to probe or have the clock application at. During this time, you essentially create higher moments of polarization states. Do you also, which should in principle create AC Zeeman shifts or quadratic effects? Do you also take that into the quadratic Zeeman effect uncertainty in the shift calculation, or this is not a big factor that you?
So I'm not sure I understood correctly these higher polarization effects. What do you mean by
polarization moments? Essentially, so
polarization moments, where would they come from?
So when the entire electronic cloud is being divided between two.
Okay. So you mean they have like van der Waals interactions between the
yeah.
atoms? Yeah, okay. So those are actually negligible because they're very far apart. The distance between the ions is 5 micrometers, roughly, that order of magnitude. So polarizability effects are super small between the atoms. Even with neutral atoms that can get down to a couple of 10 nanometers distance, you need to get them extremely close to see any dipole-dipole type or polarizability effects between the atoms.
But since they are in a bound state, and if you polarize the electron cloud,
yeah.
that should also add to this kind of effect.
Yes, absolutely. Yeah. So we use ion traps. So it's the electric field of the trap. interacting with the charge of the atom. And that's a very strong confining force. But of course, we have oscillating electric fields that then interact with the internal structure of the atom through the polarizability, as you were saying. And that's an AC Stark effect that we do have to take into account. And it is taken into account, but it is so small that it does not appear here, but it's rather on a part of the other shifts. Yeah, so it's I think 2 orders of magnitude smaller than any other shift on this table. But for other systems, you do have to take that into account. Yeah, that are not as insensitive to polarizability effects as aluminum is. Absolutely. Yeah. Yeah.
Quick question. So why there is no units in shifts? So you're measuring the transition, right? Optical transition between the states,
Yeah.
but it's like in electron volts or nanometers, but here you put no units.
I did not put what?
Put no units into your...
Oh, it's fractional frequency uncertainties always. So it's divided by the transition frequency.
And also, just a quick check on the mass. So if you combine all the uncertainty coefficients, right, it will not build up to 1.4.
I do. I hope. Well, you have to square them, sum them, and take the square root afterwards because we assume they're all uncorrelated. And if that's wrong, yeah, I will.
Just because let's say if you sum up first 3, right?
Yeah.
You will get more than 1.4.
Not if you square them. And if you do, then
okay.
I have to talk with my PhD student because I copied the numbers from the first draft of his PhD thesis last night into the slide.
Okay. Thank you.
No, they're a mixture sometimes. Yeah, I'll come to that. Yeah, absolutely. So for most of these measurements, we have what we call leverage. We can measure the shifting effect, which is again typically a contribution of the atomic coefficient and the external field. Yeah, so we can make the effect very large to measure the atomic coefficient more precisely. And we can also determine the environmental condition, yeah, by using other techniques rather than doing a clock measurement that's super insensitive to this effect. And I come to a few examples of that. Sorry?
So you isolate the conditions and then proportionate it down.
Correct for it. Yes. Yeah, absolutely. Yeah. So the cooling laser light shift here, the first line is we apply a cooling laser on the calcium ion at 397 nanometers, also a repump laser at 866 nanometers. And that's, of course, very far detuned from the clock transition at 267 nanometers. However, there's still coupling. There's a flip chart. So if this is our clock transition, spin down and spin up, yeah, in the aluminum, that's the difference here is 267 nanometers. Then this this cooling light couples here and here. So this is, for example, 397 nanometers. It's an off-resonant coupling that AC Stark shifts those two states to a new value, yeah, that is maybe here, yeah, and there. So these two levels are shifted, and luckily in aluminum, they're shifted in the same direction by almost the same amount, yeah.
You guys see something?
Oh.
Yeah, can you move it? Roll it over
There's
maybe?
wheels.
It's
So
No, I'm not asking. I'm not asking. You've seen it.
That was the one time they had an advantage, yeah, in the corner there. So here's the level in the ground state. Here's the excited state. When such a two-level system is subjected with 397 nanometer light, so this is 267, the energy is higher, then this is a red detuned light field that then pushes this level down and also pushes this level down because there's more levels up here that this light then couples to. And as it turns out in aluminum, both levels are pushed by almost the same amount. It's not identical the same amount, but it's very close. And we need to know sort of by how much the differential shift here actually is from that light field at 397 nanometers. And for this, we need to know the intensity of the light field on the atom. And we need to know the shift coefficient, the differential polarizability of the clock transition subjected to 397 nanometer light. So the differential polarizability is calculated by Mariana Savronova from ab initio atomic structure calculations. So this is a value that we get, but we'll measure in the future, hopefully with more digits than she can calculate, by making the effect super large by using a lot of 397 laser power, making the effect so large that it's much easier to measure than during regular clock operation. That's the one thing. And the intensity we get from AC Stark shifts on the calcium ion, because also there we have a clock type transition where the S state is directly resonant with 397 and is shifted by a significant amount. And through that AC Stark shift and the known polarizability in calcium, we can deduce the intensity on the ion. And since the ions are very close together and geometric arguments, yeah, we can determine the intensity on the aluminum ion and the associated uncertainty. So this is a very prime example on how we can nail down this type of shift.
Yeah. I just want to say that if you take uncertainties and they're uncorrelated, you have to, like he said, add them in quadrature. That means that you have to square those numbers, add them squared up, and then you take the square root of the whole thing. And if you do that with those numbers, you get 1.34. So there is, like, in the dots is still some space, right?
Thank you very much. Yeah.
Just checking.
Yes.
I think these lasers that are not in resonance are also the ones that you showed in the previous slides. Don't you have the population transfer to the first vibrational mode? Like, for example, what we see in Raman spectroscopy.
No, there is no I mean, it's these are. So I'm not sure what you mean by population transfer, because the next levels that are that this laser would couple to are also very far away. It's very far off resonant. There's no population transfer.
No, but if you can go back to 2 slides. For example, in the second one, no, in the third one, that it's bringing down the population from the left up, aluminum excited state. The red arrow in that one, yes.
Yeah, you mean the third?
Yeah. And then you're exciting that. I mean, technically, then you can, with that red laser, you can bring the one in the ground state to the virtual excitation and bring it back to the first vibrational mode. No?
Yes. Yeah. I'm not, or maybe I'm a bit confused.
Maybe we can discuss it later. It's fine.
Yeah.
Yeah.
So the clock interrogation is done essentially after this step here, and everything that happens afterwards does not affect the populations or the clock read the phase evolution of the clock any longer. So we can do all these pulses, and that's not a problem.
But can you go back a couple of animations? I think there was an arrow. Yes, this one that it has a cross on that red one. But can't that excite to the first state, like first emotional state, not
No. There is because that's already the ground state up here, the motional ground state, And you cannot go below the motional ground state. There's no level to couple to.
Visual excitation, like something that also in Raman spectroscopy.
But for Raman, you have a much more complicated level structure. There's all kinds of other levels. And the point here is that these levels do not exist, yeah? That you do not get this branch in the Raman transitions. Yeah. More questions?
No, like not question. Can you go back to the slide that he mentioned? So yeah, in the third animation, like is it like from that N0 excited of AL plus when it comes down to like N1, this sidewise thing, then in that case it like gives a photoluminescence of that wavelength, that downwards red arrow. What does the downwards red arrow means in this third animation?
We drive that. So it's an induced emission of photons into the laser beam that we apply to the system.
Okay,
So we de-excite the atom from the excited to the ground state. So it's induced emission, essentially.
we de-excite from N0 excited to N1 ground, right?
Yeah, from here to there. And it's a Raman process, absolutely, yeah. But it's induced emission because our laser, this arrow here, represents a laser that we apply to the system. So we can do Rabi flopping between these two states, actually. Yeah? And we just stop at the pi pulse, where we transfer all the population from here to there.
Okay.
More questions? Okay, then let's go back to this table here. So that was a cooling laser light shift, which is actually related to the black body radiation shift. Yeah, it's the same type of shift, just a different source. Yeah, in this case, it's a cooling laser that we apply that shifts the levels differentially. And in case of the black body radiation, it's a thermal radiation of the environment that leads to a similar differential shift that we have to characterize. Then a quadratic Zeeman effect, I already mentioned. You not only have the linear Zeeman effect, but a quadratic component to it. When you have nearby lying fine, hyperfine states, for example, that leads to nonlinearity, a squared dependence with the magnetic field of the shift. And we determine that through this scheme, yeah, where we measure this component, this component, and by having previously measured in a calibrated way the G factors of the ground and excited state, yeah, that you need to know. That's again the atomic parameter that you need to know. We can directly determine the magnetic field. And knowing the magnetic field, and knowing the correction factor for the quadratic Zeeman effect, which we also had to measure previously, we can apply that correction in this case. Then there's collisions. That is a bit of a problem. We have collisions maybe every 3 minutes or so during clock operation, and there's different effects collisions can have. And that's one of the problems I will ask you to solve and discuss among yourselves.
What about a better vacuum chamber?
Yeah, we tried. I mean, this is as good as it gets in our system. We have a steel chamber, which is not a good idea, but the chamber is 15 years old or so. We have a second generation system, which is made from titanium, which is slightly better, but there's a lot of crap still inside. And once we remodel, we hope to get a much better vacuum.
What vacuum pressure does it correspond to, this number?
A couple of 10 to the minus 11 millibars. Yeah, it's already pretty good, yeah. But I should point your attention to this publication here, which has come out a couple of weeks ago. That's the NIST, the latest incarnation of the NIST aluminum clock, which has now been evaluated to 5.5 times 10 to the minus 19. It's the most accurate published clock so far. And what they did is they attacked exactly this collision problem. They have a titanium vacuum chamber, super clean inside. They have, I think, in the range of low 10 to the minus 12 to 13 millibar pressure in there. It took a lot of effort.
Also, just put it into 4 Kelvin
Yeah.
helium bath.
Yeah.
That would freeze out all the.
That's what we do with our highly charged ion experiment, where we do not have collision problems. Yeah. But the fact that this uncertainty is so large is that we do not have a proper model yet for what actually happens for the collisions. And maybe you have a good idea how we can solve that. That's why I put it as a question. Then there's a thing called micromotion that we have. So if the ion is not perfectly in the center of the trap, yeah, but if you have a DC field from patch potentials that pushes the ion radially out of the trap, then it feels the driven motion by the oscillating potential that keeps the ion trapped. And it moves the ion around. That has two effects. The first is excess motion, yeah, it's kinetic energy, second order Doppler shift, which is a problem. And the other one you mentioned before, it's an AC Stark shift because it also feels an oscillating electric field that again leads to a differential polarizability. So the effect is small, that's why it's not on the budget, but we do have a second order Doppler shift from this excess micromotion. We can correct for that, of course, when we measure it happens. And this is a prime example of how we can use other measurement techniques to constrain these type of effects. So micromotion, we do not need to measure via its effect through the second order Doppler effect, but rather we can do sideband spectroscopy. Maybe I should draw that again. So if I have a spectrum, an excitation spectrum of my ion, then I have here my clock transition in the center, that's F0, that's the transition I would like to drive. But when the ion is moving, then I get sidebands. Yeah? If you transform that into the frame of the ion, then the motion through the linear Doppler effect generates sidebands, left and right. And if it's moving at let's call it capital omega RF. This is the trap drive frequency with which we operate our ion trap. Then we can actually, we see that on the spectrum. So this is a clock transition, and if we have micromotion, and we see sidebands here that we can then minimize. And we can actually calculate very well how the interaction looks like. And we know that when we minimized it to a certain extent, then this is the level of micromotion or second order Doppler effect that we have to account for. So we do not need to average down to 10 to the minus 18 to constrain this shift. It's just a service measurement where we need to probe these micromotion sidebands during the clock cycle. And since this is drifting on a very slow time scale, it's sufficient if we measure it every half hour or so, roughly. And I'm not sure if you have seen it. Yeah, so this is how it looks like, yeah, with the sidebands. Okay, then there's phase chirps from switching the clock light on and off, yeah. The acousto-optic modulator has a crystal that can warm up. There's different effects that you need to take care of. There's no phase chirp that would look like a linear Doppler effect. Black body radiation, we already discussed. Quadratic Zeeman is again from the charging currents of the trap that we have to take account for. Then the clock laser Stark shift is a question. Why do we get a clock laser Stark shift? At all. And then the second order Doppler shift is from residual thermal motion because we're not perfectly in the ground state, but at an n bar of 1 to 5, depending on the motional mode that we're looking at. But due to the fact that we are laser cooling during interrogation, the uncertainty here is super small. Yeah, it's almost negligible. Any questions to the error budget table? Then we move on to the performance of the clock. We ran this clock with 250 milliseconds Ramsey dark time, which is very long. And at the time when we did the experiment, that was actually a record for an ion clock, because nobody had this super duper silicon cavity stabilized laser that we have at PTB. And the corresponding coherence time that would allow us to probe for 250 milliseconds. And therefore, we saw an instability averaging down here with 6.6 times 10 to the minus 16 at 1 second, yeah, or per square root of tau. And that is compared against the strontium lattice clock at PTB that runs at many atoms and has an instability that's even slightly lower than this value. We do sympathetic cooling during the probing, and that is a trade-off between the time dilation shift, which would be larger if we didn't do the sympathetic cooling, and the stark shift from the cooling laser. And we believe that the stark shift from the cooling laser can be constrained much better than any dynamic changes in the time dilation shift, which is much more cumbersome to measure and monitor. And so in all, in situ cooling efficiency, micromotion, and B field monitoring and so forth amounts to 6% duty cycle, where we actually probe the atom. Okay, that brings me to the summary of the aluminum clock. And now I need to check the time. How much time do I have? In 8 minutes or so? Yeah, okay. Then I'll cut it short. Yeah, I'll give you the choice what you want to listen to. So that's the summary. The NIST aluminum clock is currently the most accurate published clock in the world. There's a Chinese calcium ion clock that is slightly below that. It's at 4 point something 10 to the minus 19 evaluated, but not published yet. Yeah, so it's on the archive. So maybe this becomes the best clock in the world. We don't know yet. So we know very well what to do to go to 10 to the minus 19 at least. Beyond that, it might turn out to become more and more difficult. There's current discrepancies. That's not the only discrepancy I should mention. Yeah, that does not stick out. It's a common theme that when we do these European frequency measurement campaigns, that there always has to be a dark uncertainty introduced, because the evaluated error budgets do not match the frequency ratio measurements, and they do not agree within the expected uncertainties. Which means that we need to be much more careful with our error budgets. Yeah, there's undetected effects that still shift the transition frequency that go unnoticed, and we need to find out what that is and eliminate it and characterize it. Yeah? So there's still a lot of work to be done. Okay, and yeah, that's essentially the summary. And now you have the choice: either I show you a multi-ion clock using dynamical decoupling, or I show you how we established maybe the first entanglement enhanced optical clock. What's the vote? Dynamical decoupling, hands up. Entangled ion clock. You voted twice. But I think that's more people. So maybe let me jump through that to that real quick. Okay. So an entanglement enhanced clock. I was already mentioning the Chinese group. They have built a calcium ion clock, and concerning the properties of calcium as a clock ion species, it's actually very bad. Yeah, because the polarizability is fairly large and it has a huge electronic Zeeman effect. Yeah, that it's 1.4 megahertz per Gauss roughly. So it's huge. And that's a problem, yeah? So it's in SI units, 10 megahertz per millitesla, roughly, or 14 or so, which means that you would need to stabilize the magnetic field down to 100 picotesla to get only 1 hertz of line width shift, actually. And that's very difficult to achieve experimentally, not impossible, but very difficult. This is a level structure of calcium. This is a D state. It's metastable. It lives for 1 second. And we have here 10 megahertz type shifts and here 8 megahertz type shifts between the Zeeman states here. Now, an elegant and one problem is the averaging that I showed you for the aluminum does not work particularly well here, because it's so sensitive to the magnetic field that between the probe cycles the magnetic shift has already changed by too much, so that you cannot rely on the magnetic field being the same when you probe left and right, and that's a problem. So why don't you do it simultaneously? So you can do that. And an even more elegant solution is to use two ions and entangle them in a magnetic field-free state. That looks complicated, but it's really not. So we have two ions in the trap in this case, and we generate through the sideband pulses that I have been showing you. You can form an entangled state where one part of the wave function is represented by one of the ions being in the Mj minus 1/2 state and the other ion being in the Mj plus 1/2 state. And this state here, since it contains Mj plus and minus 1/2, is free in the magnetic field shift. So there's no magnetic field shift there because both levels shift in opposite direction, nulling the average energy is the sum of both, nulling any magnetic field effect. We can do the same in the excited clock state. Here, again, entangle the ions in a minus 1/2 and a plus 1/2 state, but this time in the excited clock state here. So the phase evolution that we have between these two parts of the wave function is given by the energy difference, and the average energy difference, there no longer the magnetic field appears to first order. It's just twice the transition frequency. So this is a GHZ type state, or it's also one of the belt states, just in a different manifold that is free of the magnetic field shift, and we call that a DFS, a decoherence-free substate or subspace. So it's free of the magnetic field shift, and it evolves at twice the optical transition frequency. To demonstrate that that actually works, we compared the coherence time that we have under regular operating conditions of a single atom, where we have this large shift. You can see it's a millisecond coherence time roughly, and the entangled system in a DFS, you can see it also goes down here at 500 milliseconds. We have 0.4 contrast or so. But it's on this dashed dotted line, and the dashed dotted line is the contrast that you would get just from spontaneous emission of the two excited states. So we are excited state limited here and could increase the coherence time by a factor of 500 from this 1 millisecond. Okay, you can also have classically correlated states. I'm going to skip that. The gist of it is this here. It's also free of the Zeeman shift, but you get only half the signal, and so there's no entanglement. There's just classical correlations between the state. So it's in essence, you have one part of the wave function that's just giving you a background of 1/2 excitation, and then another part that looks exactly like the previous entangled state, but the overall state is not entangled in this case. And we run a clock against the strontium lattice clock at PTB, and using these entangled and classically correlated states, you can see that the entangled states always are below the classically correlated here. We could then deduce from the solid point here the scaling in terms of the statistical uncertainty, and then put that scaling into a plot as a function of the probe time that you can see here. And this is the result. So this is the interrogation time here, and this is the 1 second instability that we get. So the fit from this, you don't have to take pictures, is here in this publication. So it's a record stability for a calcium clock. Maybe I should first dwell a bit on what you see here. So you have the interrogation time here, the probe time that we varied as a function of this 1 second instability. We have here the dashed line would be the Ramsey for a single atom, n equals 2 would be a Ramsey under perfectly stable magnetic field for 2 atoms, not entangled. And the red line is what we would get with an entangled state. And we can see that everything in red here, the red shaded area, is the non-classical regime that we're, with this data point, deep in the non-classical, or not so deep, but at least in the non-classical regime. And then we're leaving the non-classical regime, but we're still better than the best classical calcium clock that has been demonstrated with it, which is this green data point here. And so we've achieved a record instability for a calcium clock of 7 × 10⁻16 at 1 second. We achieved that at half the probe time, which is to be expected. And we know that there's a limitation in accuracy because there's residual magnetic field fluctuations creeping in because we open the interferometer step by step. But nevertheless, this is, to our knowledge, the first entanglement enhanced clock that's really better than any of its classically operated counterparts, yeah, using this decoherence-free subspace. So what's the future here? Since I'm out of time, I can only quickly go through this. We have teamed up with Clemens Hammerer and his group to identify optimum probe protocols. And what they have found is that a similar type of GHC state that we have produced is actually optimal if you're limited by spontaneous emission as the major decoherence mechanism in your system. They even beat squeeze states, which people have thought would be the best state, non-classical states to use to improve the signal-to-noise ratio here. But the statement is only true if you're limited by spontaneous emission. So what you can see here is the optimal clock interferometer. That's a theoretical limit derived from the quantum Cray-Aramo bound, yeah, if you know what that is. And this is the parity GHC type protocol that we have actually implemented. And there's actually no gain over the standard quantum limit. You can do a so-called linear GHC state where you implement this entangled state and then you undo it and then you do a measurement. What we did is we did a parity measurement right after the Ramsey and not undo the entanglement operation. As it turns out, when you undo the entanglement operation and then detect, that's more efficient. You actually get a gain here. And now what Tim Kielinski found out that what you can do is you can actually measure whether a spontaneous emission event has occurred during the measurement protocol, because if you undo the measurement, then your result should be either all atoms dark or all atoms bright. That should be the result of the measurement. And if you see something in between that only a few are bright or dark, then you know spontaneous emission has happened during the protocol. You throw the data away and you repeat. And that helps you to improve actually the instability significantly. And you can change the mixture slightly, that these alpha and betas are not identical, but slightly different. And then you can see that you can actually saturate the optimum quantum interferometer using these heralded unbalanced GHC states. And as a comparison, spin squeeze states perform like this in this curve. Here you see the win over the S standard quantum limit or quantum projection noise limit. You can see that beyond some tens of atoms, actually the spin squeeze states take over. But up until then, if you're limited by spontaneous emission, these GHC states are optimal, actually. That brings me to the end of my 2 lectures. I hope you learned how optical clocks work, that they are the most accurate measurement devices there are, how you can measure them, compare them, bring them to remote places, and what you need as ingredients. And in the second part, I hope I could convince you that quantum logic is a very powerful and versatile technique that allows us not only to investigate previously inaccessible species, but also take advantage of the special properties of quantum mechanics like entanglement or full coherent control and dynamical decoupling to make clocks better and ready for the next generation. And there's a lot to be done. There's a bright future and a strong synergy between clocks and quantum information processing. And with that, I would like to thank my fantastic group for their work, the funding agencies, and of course you for your attention.